Good morning, everyone. My name is Mark Deron, and today I'll be presenting on Beyond the Liquid Limit, the solid state revolution. We are going to explore how a fundamental shift in battery technology from liquid electrolytes to solid state systems is poised to redefine energy storage through material science and electrochemical stability. This assessment task focuses on understanding the science behind these two competing battery architectures and why solid-state technology represents the future of high-performance energy storage. So let's dive in. Now let's understand the two main battery architectures we are comparing. First, we have conventional liquid electrolyte batteries. These use a liquid organic solvent to transport lithium ions between the anode and cathode. You've encountered all those batteries, and they power your smartphones, laptops, and standard electric vehicles like the Tesla Model 3 and Y. They're everywhere because they are efficient and mature technology. Next, we have solid state batteries or SBBS. The key difference is here. SBBS replace the flammable liquid with a solid electrolyte. This solid can be made from ceramic, polymer, or sulfide materials. What's crucial is that the solid electrolyte isn't just replacing the liquid, it's doing double duty. It's conducting ions and acting as a separator between the anode and cathode. This is the architectural foundation for why solid state is superior. So let's explore the specific advantages. The first major difference is safety and chemical stability. Solid state batteries achieve zero flammability risk. This is a game changer. I remember the Samsung Galaxy Note 7. Those phones they caught fire because the liquid electrolyte was flammable and could cause short circuit. With SSBs, you eliminate that risk entirely because the electrolyte is solid, non-flammable, and resistant to leakage. No toxic chemical leaks if the casing is damaged. Second, solid-state systems have exceptional high temperature stability. Standard lithium-ion batteries catch fire if they overheat or if there's an internal short circuit. SSBs, they remain chemically stable and even at temperatures above 100 degrees Celsius. This means better safety margins in demanding applications. And there's a bonus because SSBs don't need aggressive thermal management. You can reduce the need for heavy cooling systems that contributes to overall weight reduction. Less cooling system equals lighter vehicle equals better efficiency. Now, let's talk about what every electric vehicle manufacturer cares about: energy density and weight. This is where solid state really shines. First, energy density. Solid state batteries can use lithium metal anodes instead of graphite. Lithium metal is much lighter and can store nearly double the energy in the same physical volume. That's a massive improvement over graphite-based anodes in conventional batteries. Second, volumetric efficiency, because the solid electrolyte acts as both the ion conductor and the separator. You don't need a separate separator component. Battery cells can be stacked in much closer together. We are talking about a 20 to 30% reduction in total battery weight while maintaining the same capacity. In an electric vehicle, that means lighter weight, longer range, or both. Now, let me show you this comparison table, which really highlights the operational advantages. Looking at charging speed, liquid electrolyte batteries take 30 to 60 minutes to reach 80% charge. That's why most electric vehicle owners wait 20 to 30 minutes at a supercharger. Solid state batteries They have the potential to reach 80% in just 10 to 15 minutes. That's a breakthrough for practical electric vehicle adoption. Cycle life is even more dramatic. Conventional batteries degrade after 500 to 1000 full charge cycles, roughly 3 to 5 years for daily use. Solid-state batteries can withstand 5000 to 10,000 or more cycles. That's 10 times longer. And temperature range, SSBs operate reliably from minus 30 to plus 100 degrees Celsius, while liquid electrolytes are constrained to 0 to 45 degrees. The underlying reason for all this is that solid state enables faster ion conduction without degrading the material lattice. The ions they move more efficiently and there's less chemical side reaction. It's elegant electrochemistry. Now we need to talk about the three types of solid electrolytes because not all SSBs are created equal. Let's start with oxide-based systems. The most common example is LiGeTO, that is lithium, lanthanum, zirconium oxide. It's a ceramic material where lithium ions literally hop through a crystalline lattice structure. We will talk more about that hopping mechanism in a moment. Alright, oxide-based electrolytes are the safest type and have the highest voltage stability. But here's the challenge. Ceramic is brittle. Manufacturing large quantities of uncracked, defect-free ceramic sheets is difficult and expensive. That's why LiGeTO isn't yet scaled to mass production. Then there's sulfide-based electrolytes like LGPs. This is the performance leader. Sulfide-based systems have the highest ionic conductivity, comparable to liquid electrolytes. And because sulfide are ductile, not brittle, they form better electrode contact, which reduces internal resistance. So the problem, they are hygroscopic. They absorb moisture from air, and if exposed to air, they can release toxic hydrogen sulfide gas. So manufacturing requires extremely careful control. The third type is polymer-based solid electrolytes. These use a flexible polymer matrix like PEO, polyethylene oxide, to transport ions. Think of it as a solid solvent. The polymer chains form pathways that lithium ions can move through. It is not as fast as sulfide-based systems, but it's still much better than conventional liquid electrolytes. Here's why polymer systems matter. They are compatible with existing manufacturing equipment. Factories already have roll-to-roll manufacturing lines from industries like plastic film or battery production. Polymers can be processed on these machines without expensive new infrastructure. This makes polymer-based SSBs the most cost-effective to produce today, and they are flexible. Literally, polymer electrolytes can bend without cracking. They can bend without cracking, making them ideal for flexible electronics, wearables, and even medical implants. Imagine a pacemaker that's flexible enough to conform to your body. That's the application space for polymer-based solid state. Let's get into the basics now. This is where solid state battery performance is fundamentally determined. In a solid lattice, whether it is ceramic, sulfide, or polymer, lithium ions they don't move continuously like they do in liquid. Instead, they hop from one vacant site to another. Imagine a game of musical chairs, but on an atomic scale. Each hop requires activation energy to break the ionic bonds, holding them and move to the next site. This is fundamentally different from the random diffusion you see in liquid electrolytes. Alright, this hopping mechanism sounds inefficient, but paradoxically, in well-designed solid electrolyte, ion conduction can be as fast as in liquids. The reason is that the hopping pathway is optimized by the crystal structure. Ions don't waste energy moving randomly. However, there is a huge challenge. The solid interface. This is where the solid electrode meets the solid electrolyte. In liquid systems, electrodes and electrolyte naturally they conform to each other. But in solid systems, contact is imperfect. As batteries charge and discharge, the electrode expands and contracts. If contact is lost, you get interfacial resistance. Yeah, it simply means that if the contact is lost, you get interfacial resistance, wasted energy and heat. Maintaining the electrolyte contact as they swell and shrink is the number one engineering challenge in state batteries. Here is a graph showing energy density comparison based on 2024 projections. The horizontal axis is watt-hours per kilogram, how much energy you can store per unit weight. The vertical axis shows this in the context of electric vehicle battery packs. The current state, lithium-ion batteries are achieving around 250 to 300 watt-hours per kilogram. Solid-state technology already outperforms conventional lithium-ion by 40% today. We are seeing 350 to 400 watt-hours per kilogram in lab prototypes, and the target 500 or more watt-hours per kilogram. That would nearly double current capacity. What does that mean in practical terms? Today's Tesla Model 3 is a 75 kilowatt hours battery that weighs around 400 kilograms. With solid state at 500 watt hours per kg, you could store that same energy in just 150 kilograms. Or you could keep the weight the same and double the range. That's the transformative potential. So, in conclusion, where do we stand? Liquid electrolyte technology remains the backbone of current energy storage. Why? Because it's cheap to manufacture, has extreme high ionic conductivity, and we have 30 years of manufacturing infrastructure built around. It works, but it's hitting physical limits. You can only make a liquid battery so safe and so dense. Solid state represents tomorrow, by eliminating flammability and enabling lithium metal anodes. SSB solve the primary bottlenecks, safety and range. The manufacturing hurdles are real. Contact issues, scalability, cost, but they are engineering problems, not physics problems. And engineering problems get solved. Companies like Toyota, Samsung, and QuantumScape are investing billions to commercialize solid-state batteries. We are not looking at the maybe technology anymore. The transition from liquid to solid state is inevitable. In the next 5 to 10 years, you'll probably own a device powered by a solid state battery. Thank you. Here is the reference for the information.